So a plus 3 is actually to the left. So I draw the regular y equals 2 to the x. And I'm going to move this. I usually move it. I pick a spot and move that. So I'm going to move it to the left 3. So it would look like this. Alright. I can combine those sort of things. So what if it says y equals 2 to the x plus 1 minus 2? Right, from what I've said on these two, this tells me to move it to the left 1, and this tells me to move it down 2. So here's the starting one. I move it to the left 1, so I usually take the crossing point, move it to the left 1, and down 2. So it ends up like that. Alright. We went from there to a very special exponential, and that special one was y equals e to the x, because it pops up so many places. And e is about 2.7, so we're going to have this crossing point, but when x is 1, we get between 2 and 3, about right there. So, oops, not on the x, not on the y-axis. So we're going to go over 1 and up that much. So here's y equals e to the x. Alright. It's supposed to be a little smoother than that. Alright, let's go on for a topic or two and call it a night. We learned about compound interest. And that's where you start with a given amount of money called the principal, and you're going to multiply it times 1 plus the rate of interest in a decimal form divided by the number of times it's compounded yearly to the n, which is still that number, times the time that it is invested, and that will give you the amount. So that's compound interest. Sometimes this n goes to infinity, and we're actually compounding the interest continually, and then we use this formula: principal times e to the rate of interest and the time. PERT. Alright. Again, this is just a quick review of the concepts, theory basically, and we'll be doing some practical or doing problems that reflect these ideas soon. Log to the base, then we entered the logarithm. The first one and the most basic is this one, and it's saying to you, whenever you see this word, if you look closely with a microscope, it says, what exponent? If you look closely, all a log is an exponent. So it says, what exponent do I give this number to get that number? Alright, that's all a logarithm is. So what would log to the base 2 of 16 be? What exponent do I give 2 to get 16? Alright, we went from there to log rules, and I won't do the A and B form, I'll do an example. So we could take a log to a given base times an expression where you have two things multiplied. That's the same thing as writing it as 2 logs where each factor is added. So that represents one of the log rules. And what if it had been 5 divided by x? Then over on this side, we will see a subtraction sign appear. And the last log rule can be demonstrated with this expression, and the 5 can run down in front. And these work backwards as well. Using those log rules, we were able to take expressions that are long, like this, and condense them to be like this, or we took expressions that were condensed or short and expanded them. So from log rules, we were able to condense and expand expressions. All right, I'll end tonight with graphing logs. And we learned that this one is y equals e to the x. And if we reflect that across this line, it looks like this. And that's the basic shape of a log graph. So that would be y equals log to the base e, or ln of x. So that base is e, 2.7. So if I wanted to find y equals log to the base 2 of x, I'll do a couple points. I'll do, what exponent do I give 2 to get 1? And what exponent do I give 2 to get 2? So those point 1 over 0 up, so that points on all of them. This is 2 over 1 up. So that would be y equals log to the base 2 of x. Well, y equals log to the base 10 of x would be very close to the x-axis. It would be way bent in. All right. We'll pick it up next time. We'll practice those things in class and pick it up next time with the more recent topics, solving log and exponential equations and using log models. All right, I hope that you find this helpful when our test arrives. Till then, or till tomorrow, good night.